Hello everyone, welcome to my talk. I would like to thank the organizers for giving me such a good chance to introduce our recent work. In this work, we explore the microstructure of a statistical volatility model with self-exciting jump dynamics. We first provide some empirical evidence. Look at these figures. At the right point, there were some events happening. We notice that around each red point, the volatility will fluctuate a lot. For example, at 2008, when the global financial crisis happened, the volatility will change a lot. Detailed during this period, we see that there are many jumps in the volatility. We record the jump with this original orange point. We find that the jumps try to cluster. In order to describe and study this phenomena, we establish a mathematical model. We call it as Hawkes-Marx model. In this model, we split the orders into two types. The first type we call it is exogenous orders. Second one, we call it induced orders. We record the arrival of these two types of orders with N. And G, we use G to record the price demand changes resulting from the order. Thus, the log price PT can be given by this formula. The blue part means the impact of the buy order. The right part means the impact of the sell order. Okay, we now give some assumption on the jump processes. We assume the exogenous order is described by two Poisson processes, and the induced order, arrival of the induced order, is described by two marked Hawkes processes with common intensity, Vt. And Vt is given by this formula. For the first part V0 means the impact of orders before time zero. And the second part in the impact of the exogenous orders. And the third part means the impact of the induced order. And X means the impact of the order arrival. Okay, all right. We introduce another two Poisson random measure. The first one, NE, it is used to record the arrival and the impact of the exogenous orders. The second Poisson random measure, NI, used to describe the arrival and the impact of the induced order. Now we can write the Hawkes-Marx order model PTVT into the following form. Especially, the first two parts, NE, means the impact of the exogenous order. Okay, NI means the induced order. Okay, because the exponential function satisfies this formula, then we can write the Hawkes-Marx order into the following form. And the existence and the uniqueness of a strong solution to this system follows from theorem 6.2 in Poisson and Lee, 2006. Moreover, the solution is an affine processes. Okay, now we study the genealogy of the market dynamic. If there's no exogenous orders, that means VE U equal to 0. Then the market model tends to be self-enclosed. We denote it as a P0 and V0. It satisfies this system. For the case exogenous order with arrival time tau ke, it will generate an self-enclosed submodel. We denote it as PK, VK. Okay, it satisfies this system. We find that this sequence of a self-enclosed submodel PK, VK are mutually independent and conditional RID. Moreover, our market model PTVT actually can be write into a sum of a sequence of a self-include submodel. Okay, that means the submodel P0, V0 forms the building block of our market model. Now we study the scaling limit. We consider a sequence of a market model P and Vn with parameter like this. And there's rescaled model satisfies this stochastic system. We assume through that the compositor of these two Poisson random measures satisfies this. This means that in the nth market model, the arrival rate of the exogenous order is gamma n, and the arrival rate of induced order is n times gamma n. This is justifies our interpretation of induced order as originating from high frequency trading. Now we consider the weak convergence. We denote An as the generator of Pn and Vn. We can get the weak convergence if we can find a generator A with domain dA such that ANF will convert to AF for any f belong to dA. For the exponential test function, we can give an explicit representation for this. Okay. At the same time, we can find a candidate limit operator A with respect to the exponential function. Based on this, actually, we can find out the limit operator and the limit generator A acting on F according to this formula. Okay. All right. Unfortunately, the linear span of the set of exponential functions is not dense in dA. Moreover, the volatility V may have no finite moment of any order. So we cannot get the weak convergence directly by proving ANF converts to AF for all F belong to dA. So in our work, we prove the weak convergence of the rescaled market model using the general convergence result for infinite dimensional stochastic integral established by Kurza and Prutter in 1996. Under some mild conditions, if the initial state converges in distribution, we see that the rescaled market model will converge weakly. And the limit model is the unique strong solution to this stochastic system. And with W1 and W2 are two independent white noise, N1 and N0 are two Poisson random measures. Okay. At the same time, the mean reversing level A can be viewed as originating from many small shocks of insignificant magnitude. Okay. Now, if we can find two correlated Brownian motion B1 and B2 such that the limit market model can be considered as a unique strong solution to this stochastic system with the white noise replaced by these two Brownian motion. Okay, actually our model contains many popular volatility models. For example, without jump, our model will turn to be Hessian model. If the jump is a compound Poisson with a Pareto distributed jump, then our model will turn to be Pareto jump diffusion model. Okay, if the jumps are two stable Levy processes, then our model will reduce to generalized alpha stable Hessian model. All right, now we studied the genealogy of the limit model. We noticed that the characteristic of function of the limit model can be split into three parts. The first part comes from the impact of all events before time zero. The second part describes the impact of the exogenous order of a significant magnitude. The third part describes the impact of the exogenous orders of insignificant magnitude. Actually, we can establish three independent stochastic systems, P0, PE, and PA, to describe these three parts. Okay, these three parts. All right, For example, P0, V0 means the impact of the event before time 0. All right. Now we study the jump cascades. Let A be a set, okay? We denote TA as the arrival time of the last jump with magnitude in A, P0, V0, all right? And GAT be the number of jump with magnitude in A during the time interval 0 to T. We find that if B2 positive, we find that the probability of the arrival time of last jump larger than T will decay to 0 at some exponential rate. If B2 is negative, this probability will convert to a positive constant. If B2 equal to 0, then we find that the probability will decay to 0 at some power law. Okay? All right. Now we compare the endogenously and exogenously triggered jump. We found that the expected number of jump in submodel P and VA, okay, it will decay to 0 at some square root T square as T go to 0, and it will go to 0 as T go to infinity at some linear rate. By contrast, for the exogenous triggered jump, their expected number of jump will decay at some linear rate at T go to 0. This tells us that exogenously triggered jump are more likely to occur shortly after the exogenous event, and hence to cluster. It means that, for example, when there's a exogenous jump here, then there's a cluster follows the exogenous event. Here also a cluster follows another exogenous event. Okay, this is all the things we want to introduce. Thank you.